We present a method for cloning the human eye from photographs and a method to render the model in real time using graphics hardware. The eye is a complex organ made up of multiple translucent tissues. We propose a simple and fast method to recover the iris structure as well as the properties of its layers. We capture 2 photographs of the iris and the environment lighting. We can then perform comparisons between the photographs and the rendering of our virtual eye. We first automatically adjust the captured environment reflected by the virtual cornea so that it matches the actual corneal reflections of the photograph. When taking a picture of an eye, the iris image undergoes a refraction at the interface between the cornea and the air. As a result, the photograph represents a deformed iris. We first propose to unrefract the photograph to recover the original iris image. The unrefracted iris image represents the iris lit by the environment. We divide the iridal thickness into 2 parts, a generic part derived from the anatomical data and the specific individual variations that we estimate using our unrefracted iris texture. However, like most organic materials, the iris is translucent. Therefore, the surface details of the iris appear blurred due to the light scattering. We propose to compensate this natural blurring by deconvolving the unrefracted image. The variations of the thickness of the stromal layer are directly linked to the appearance of the iris. In the thick areas, the iris appears brighter. The thin areas result in darker features. Using this knowledge, we reconstruct the structure of the iris and then search for the pigment concentrations within it. We use image comparisons to estimate the iridal pigment concentrations. As we cannot exactly match the real image and the rendering, and in order to neglect the errors made in the iris reconstruction, we apply an orthoradial blur to both the rendered and the captured images. As the iris is overlaid by the cornea, the incident light gets refracted before reaching the iris. We introduce a refraction function. For a given point and a light direction, our function returns the actual optical path through the cornea. As the cornea is symmetric around its vertical axis, we only need to sample points along a radius of the iris. The refraction function is then stored in a texture for rendering. Under grazing light conditions, caustics may appear on the iris. Following the idea of the refraction function, we developed a caustic function to handle these in our real-time renderer. Here are some examples of virtual eyes under different lighting conditions.